So please feel free to ask questions, and let me share the screen. So you can see
Yes, sir. Screen is
and
visible, sir.
okay, and I am audible also, right?
Yes, sir. Yes, sir.
Okay, so today I just start now. So today I will talk about quantum computation model, basically two of them. I mean, gate-based model and adiabatic quantum computation. So this gate-based model, IBM and Google and such company uses, and this adiabatic quantum computation model this D-Wave company uses. So these are the two models. I mean, there are also, but these are the two model. Model means like, how you do the computation. Okay. So let me go slowly. I mean, um, I will tell you basic element of quantum computation. So basically, these are the three main elements. In any quantum information or in quantum mechanics, in physics. So first is initialization or preparation, you can say. So this one I'm talking about here. So, so in the first element is how you describe the system, right? And then second is how you describe the process of, like information processing. And third one is how you do the readout. These are the three basic elements. Like when you study quantum mechanics, and these are the three basic elements. So, how you describe the system is you describe the system by these things which we call cat. Cat is basically like a vector, or you can say column matrix, right? So this is the quantum mechanics. Everything is linear algebra. In linear algebra, you see the matrices and vectors. Vectors, column vector. This is the column vector. So, and you can say this is qubit. What is qubit? Is a two-level system, right? Two-level system or two-dimensional stays in two-dimensional space, 2D basically. So which need two numbers, and in quantum physics the numbers are complex numbers, right? So here A1, A2, so you can think this as a column vector where A1 is the first entry, A2 is the second entry. Okay. So initialization is like when you want to do computation, you prepare your system in state, right? So here it can be this way or it can be in this way. So this is we call basis encoding, because this is basically like when you have bits, right? Bits are 0 and 1. When you're talking about single bit, it can take either 0 or 1, right? So this is this if you can prepare only 0 or 1, then this kind of encoding is called basis encoding. And when you can take a linear combination of that, linear combination is a mathematical term, which in physics we call superposition, interference, or I mean, these are things. Basically, it is a linear combination. You just take A and B. But the main important point is this is not any linear combination, these two, 0 and 1, would satisfy this condition that absolute value and square is and then you add these two one. So what is the meaning of this one is this is a probability, and because the absolute value of any number is a positive number and square is also a positive number, so probabilities are positive.
Hello, sir.
And hello.
Sir, sorry for the interruption. Sir, please zoom your screen, sir.
Okay. Yeah, maybe now it's clear.
Yes, sir, it's clear. Thank you, sir.
Okay. Yeah. So if you perform, I mean, in linear algebra, you also have bases, right? So in quantum mechanics, each basis describe a measurement, right? So 0 and 1 make one basis. So if you perform the measurement in 0 and 1, then you will get outcome 0 with this probability. So this is the probability of getting 0 outcome, and this is the probability of getting 1 outcome. So each probability add up to 1, right? So this is the basic thing, is they are probability and they add up to 1, right? Now this kind of encoding is also called amplitude encoding, because these A1 and A2 are amplitudes. This is like a just wave, right? In wave you have when you study wave, so they have amplitude, electric wave or water wave you study, but it is in space, so things are continuous. So here things are discrete and the same concept. So if you want to describe wave equation, you can describe differential equations, which is linear equation. So it's a linear algebra is there in different form. Here linear algebra is discrete. So, and basically everything same. So this is how you initialize system. You can initialize like this, but this is more general. So consider this part, because this is more general amplitude encoding. So this is how you describe a system. There is a much more general approach also, where you take positive matrices to describe a system. So this is a vector. If you take this projector for this vector, that will be a positive matrix. So you can describe more generally with a positive matrix. Positive matrix have all the eigenvalue positive, and then this condition will correspond to trace is equal to 1, which basically says that if you perform any measurement, you will get a probability which are positive numbers, and then they will add up to 1, right? So this is much more general description of a quantum system, but for this presentation, this is good enough. Now, process, right? So you go from one vector to another vector, right? And through a unitary transformation, because you want to conserve the probabilities, right? Right. So to which transformation conserve the probability is a unitary transformation, right? In more general terms, if you take positive operators, then it will be a CP-TP map. A CP completely positive and TP means trace preserving, but much more general, so I will not talk about it. So unitary evolution is a special case of CP-TP map. So basically, you go from psi initial to psi initial to psi in to psi out, and you can think of as a matrix multiplication, but matrix must be unitary. Okay. So unitary matrices are those which preserve inner products. So this probability you get with the taking inner products, right? So once you have output, you perform measurement, right? So you can perform measurement in any basis, and then you will get this two outcomes, because two level system. So there are only two possibilities, and if you perform measurement in this direction, you can get either up or in down. So one more thing I want to describe, which is very important. So this process, I just put different arrows here, basically means like this process is reversible and this is unitary, and this process is irreversible, right? So once you perform measurement, you can go back to this psi out, right? So, but you will get these outcomes, right? So let me describe taking a single qubit. In case of single qubit, two-level system, I mean, Nagendra told you in his presentation, you can realize in many ways, like you can think as an electron in a magnetic field, you can think as a polarization of a photon, and you can take this time cube. So there are many realizations, but basically, for mathematical point of view, this is a two-level system. So you can describe any two-level system state on a unit sphere, right? So it's a x, y, z, and these box are this length is unit. So it is unit sphere of a radius 1. So suppose my initial state is this one, which is 0. So this is x-axis, right? So on this x direction 0, 0, 1. This is x z direction. Sorry, this is z direction. So north pole, you can think as a globe. North pole is a 0 state, and south pole is 1 state. So any two antipodal points correspond to two this such states, like a spin up and spin down, right? Because okay, so and when you apply transformation like this process, then you go from green to red. For example, in this case, your psi out, which is denoted by this red point here, is cos theta sine phi. So cos theta 0 and sine theta 1. So here a1 is cos theta and a2 theta, right? After process, okay. So this sine, and then when you perform a measurement, you use a direction, right? For example, for simplicity, I just choose the same measurement along z direction. So it's basically the projection of this final output state. So the outcome will be either 0 or 1, but the probability is given by the component, which is like cos theta in this case, right? Probability is a cos theta square. So you will get this 0 outcome with cos theta square probability, and you will get this 1 outcome with sine theta square probability, and they add up to 1, of course, right? So this is basically how you describe, you evolve it, and then suddenly this point will jump either here or here probabilistically. But once it jumped here, you don't know where this point is come from, right? So once you get this one, and then you don't know where if I don't know what is psi out, then you don't know where this outcome come from. Okay, so this is a probabilistic nature. And if you perform, you take 100 particles, and the cos theta square fraction of them will come here, and sine theta fraction of them will come here, which basically means the probability. Okay, so you have to prepare many particles in the same state and perform measurements, and then you will get this distribution given by cos theta square and sine theta square, right? Probabilities. This is a basic part of basic element, how you describe the system, how you describe the process, how you describe a method, right? So more details you can get in these books. So this is book on quantum computation. Have some element about quantum mechanics, and this is a book like a recent one, which also describes some recent algorithms, like which is related in quantum machine learning and other stuff, right? Okay, so I go next, right? So first I will first talk about gate-based quantum computation. So now I am only focusing on this process part, right? Only the process part. How you realize this process, you realize through gates or you realize through adiabatic evolution. So that's how the two way of computation model differs. So so let me take first example. So in your input initialized state is 0, which is basically north pole, right? This green point. And then you apply this transformation, and this is just a unitary operator. This is a rotation, so rotation is a unitary operator, and this is based on the angle, right? So this is a rotation around y-axis. You can see this is a y-axis. So this is y-axis. So it's a rotation around y-axis by 2 theta angle. There is a theta, and here this angle is 2 theta, which is because the spin half particle. So the rotation here, the theta, it will correspond to theta on globe sphere, right? So much more technical terms, like there is a isomorphism between unitary group O3 SO3 and the orthogonal group SO3, and then special unitary group SU2, So this is because of that isomorphism, right? So basically, so it takes the input vector, which 0 in 0 1 basis is like this column vector. So this unitary transformation, which change 0 in this way, is in these bases 0 1 basis is written like this, which is a rotation around y-axis by 2 theta angle on the block sphere, 2 theta angle on the this two-dimensional space, because this is three-dimensional real space. So this is a two-dimensional complex space. Okay, so just because of the isomorphism, right? And then you get this final output vector, which cos theta sine theta, right? So this is a rotation from red to green. Now this is a gate, we call it gate, unitary gate, which is by angle theta. Then second thing is, imagine now you apply this V gate after U gate. So your input will be this vector. So this vector, which is output from the first gate, will be the input in the second gate, right? Now you apply rotation about z-axis, right? So this is a z-axis. So this red point goes to blue, right? So your red point is this input, and then you apply this V gate. So you give the rotation about by angle phi. So then your the output state is cos theta sine theta e raised to power I phi. So this is the most general state you can write. You only need two angles to describe any point on this unit sphere. So the most general state is uh, for a two-level system is like this. You can write any state in this way, and you can say C1 is normalized. Normalized means like it satisfies this constraint, right? You take absolute value. So so that's how you can create a most general single qubit state, single. And now the another, in another words, like so taking these two gates, right? You can make any single qubit gate. You just put them in a sequence. You can decompose any rotation in combination of these two rotations, right? So these are the basic, whenever you see this S gate, T gate, and these are basically these two gates, one of these two gates, or combination of them, right? So you just, because product of unitary operator is also a unitary operator, so you just take, you put them sequentially, so it's basically product you will get. So that's how you just go 0 to this state, and then this goes to this state. So this is how you perform by unitary evolution, which is basically gate-based quantum computation. Now for single qubit, that's all for the process. Now I go for 2 qubit. So if you have some question, you can ask me. And if you don't, if I am not audible, you can also tell me. Now I go for 2 qubit gate. Like this, all the unitary operations, all the operations on quantum information can be decomposed in single qubit and 2 qubit gate. That people call it universal set, right? So now I will describe one 2 qubit gate. I mean, that is enough to make the universal set. So you just combine these two and this one gate, and then you can realize any of the any of the unitary operations, any of the evolutions, right? So everything is made of these three, 1, 2, and 3, right? Now, what is this gate, right? So this gate is like, let me describe this full process first. So now we have 2 qubits, right? And one more thing I want to say is, like a single qubit, you can describe them geometrically like these block spheres. But in case of 2 qubit or higher dimension, if you go beyond 2, then it is really difficult to visualize it. So you have to really do this kind of algebra, and there are some ways to realize it, but like so in case of single qubit, means single two level system, everything is there. But in two, it's not there. You cannot visualize it. But everything you can do, you have to do computation like this. So you have two qubit or spin, and then each one of them are in 0 0, like initialize in 0 0. Then you apply this operation, which is basically this gate biangle minus pi by 2. So and when this is pi by 2, then it's 1 by under root 2, 1 by under root 2. So you will get this state, but you don't do anything on the second qubit. So you don't do anything on the second qubit, it stays as it is. So at this point in time, so here you are going from left to right is, time, right? So in this one, there is nothing, it stays as it is. Now this, when this open dot means like you take 0 as a control, and then you apply X operation. X operation is basically this flips 0 into 1 and vice versa, right? So it takes 0 as a control. So it takes 0, it flip this 0, second one, into 1. And then it don't do anything when the control is 1, and it flips when control is 0. Okay. So this, we get this state. This in atomic physics or called singlet, right? And this is in quantum information also called Bell state, and this is a example of entangled state, and that's how you get entanglement. So this is the basic circuit or basic process that you do. You generate Bell state. So what is the use of, and this is the gate which generate like a correlation, right? So I will explain you what is the correlation here. I mean, you can see that if you perform measurement in 0, if you get 0 outcome, the other one will be 1 outcome. So there is a 0 and 1 are correlated. If one is 1, another is 0. So it's anti-correlation, right? So, but like, let me explain you a bit more in detail what is correlation here. So where we can use this 2 qubit state, right? So basically we use for quantum cryptography, right? So this is basically the scheme I am telling you. What is the quantum cryptography? So you want to send a secret message from Kolkata to Bangalore, right? And so from Delhi, this is a service provider from Delhi. It provides you these 2 qubit, like it perform this operation, and then this operation, then it get a Bell state. So 1 qubit goes to Bangalore, another qubit goes to Kolkata. So this, you can call it quantum channel. So when you hear talks and then they talk about, so such a channel is called quantum channels, where you have, in case of optical fibers, how you do it, you just create these 2 photons which are entangled in this state. So, and then 1 photon goes through optical fiber to Bangalore, and another goes to Kolkata. Now they share this entangled state, right? So that's how, when you listen to some other talks or read some papers or books, so this is what one of the quantum channels. Okay, so how they do? So they choose to measure their own qubit in some direction, right? So each direction on a Bloch sphere represent 1 measurement setting. They choose same measurement setting if they choose same measurement setting. So if the Bangalore one get a spin up direction, then the Kolkata will be spin down, right? If it is spin down, then it will be spin up in Bangalore will be spin down, and then Kolkata will be spin up. And then if you generate such 100 pairs of particles, so you will get such a sequence of the data. You can see that if you look at the individual sequence, like at the top 1 row, then it is random, up, down, 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 up, and so on. Then if you look at the below one, it is totally random, right? There is no information there. but if information is in their correlation, right? So if one is spin up, definitely the other one will be spin down, right? So if Bangalore encode, so you can see this is a 0 1 0 1 1 1 0. Spin up is, let's say, 0 and spin down is 1. So similarly, so this is a key to encode information, and these two things are correlated. So this is a key to decode information, right? So if Bangalore want to send some information to Kolkata, then Bangalore take this thing to encode information and then send to Kolkata, and Kolkata take this key to decode information, right? So and the important point here is this correlation, such a correlation is possible in any direction, provided they choose the same direction. So if they choose this any other directions to measure their spin, so you will find the same correlation, provided they have these two are in the same direction, right? So this is much stronger correlation. So that's how you do secure communication. The people talk about quantum communication. So this is the basic thing. So how it is secure, why it is secure. So I will not tell, I haven't put anything here to describe that thing, but let me say one line that there is a principle called Heisenberg uncertainty principle or relation, which in some form is basically means like information disturbance. So if you extract some information from this channel, then you disturb the channel, right? So, and that disturbance can be seen. Like for example, the point of hacker want to hack you without being detected. So if you detect your email is hacked, you will change your password, right? So you will stop communication. So the point here is like if somebody this network try to take some information, you will find it trace, and you will stop communication. Basically, you will change your password, right? So is secure. So it's a basic principle of quantum mechanics, Heisenberg uncertainty. One side is security, which I have said here anything. So because it's a bit technical, I just tell you how to generate key, right, and how to use it. But wide security is Heisenberg principle, and this is application, right? And here I forgot to tell the first slide one of the applications. Have any output state, you if you perform measurement, you get this spin down, right? A random number, it give you 0 1 0 1 with these two probabilities. If these two probability one half, then it is totally random number generator. So such a random number generator Samsung put in their mobile phone, so these random number generators are very useful because you get one time, right, when you want to buy something online, or you want to make bank transaction, right? So this OTP are used, but they are come from your random number, which is a long sequence, and then, but this is a pure random number, right? It's just quantum mechanics, and then like that's how you can generate random number, right? So one application random number here, and then application I told you quantum communication. Such kind of nodes, like you can make a long sequence of communication. Okay, so this protocol is based upon this Eckert, and there is another protocol called BB84. So B is Bennett and this one, and 84 because it's published in 84. And by the way, it was this conference was in Bangalore when this happened. But anyway, I go next, right? Another application is a quantum Fourier transformation, right? So we know that this is a how you do Fourier transformation. So you have a column of complex numbers a, and let's say they are n of them. So it's a column vector, and then you apply this, and then get a bk, right? So another column vector. So Fourier transformation you need. And to complete this one, you know that for full precision, you need 32 bits to store any real number. And since this is a complex number which requires two real number, any complex number can be described by two real numbers. So you need that many bits to describe one complex number. And since there are n of them, you need that many bits to store these. And since the Fourier transformation is a sparse matrix, so you need n log n number of operations to perform this discrete Fourier transformation. So there's a algorithm called fast Fourier transformation. Now, in comparison to this one, what is quantum Fourier transformation? So quantum Fourier transformation is just this is, can be viewed as a change of basis, right? Because you have one basis, A basis, which have n vectors, and JA vectors become B vectors, right? So, and then this transformation, right? So why people call fast, right? Exponentially fast is because of this thing. Because if you have 50 qubit, right, then you are basically processing 2 raised to power n numbers together because they exist in superposition, right? So that many numbers to process, if you have these A's are that many, right, then you only need 50 to process on a quantum computer, right? So that's why this is exponentially fast, right? You can see these are that many numbers is also difficult to store on a computer. I mean, like if it is like 1,000, I mean, like then like these are too many. I mean, like so that is the power of a quantum computer because it considers the superpositions. So for n qubit, there are 2 raised to power n possible states, and you can take the superposition of them, and that's why it is exponential speed up, right? So first, this quantum Fourier transformation, which looks same, but only the power comes from this part because you can write this n into 2 raised to power n. Okay, so this quantum Fourier transformation is a very important part of Shor algorithm. Shor algorithm is used to factorize complex numbers into prime factors, right? Because if I give you two numbers with prime, you cannot factorize them. You can multiply them and give opposite number. So multiplying is easy, but factorizing is so difficult. So that's why this cryptography, like you send message from one place to another place. So you you do encoding using this factorization because factorization is difficult. So breaking your code, breaking your message or hacking your email is difficult because the underlying principle is factorization because factorization is difficult. Because this Fourier transformation is exponentially fast, you can do factorization through Shor algorithm. So Fourier transformation is a part of the Shor algorithm where you can do factorization. And since your communication, you sending emails based upon the factorization, you can do factorization, then somebody can hack your email. So that's why this is also power of quantum computer. That's why people want to build it. Now see, on the first one slide, quantum mechanics provide a secure communication. And also now in this slide, see the quantum mechanics provide, like breaking of a code, breaking of an email password, right? Because factorization is on which the security is based on, right? So now in this Shor algorithm, one of the main element is phase estimation, right? So let me describe a very basic idea of phase estimation. What is the phase estimation? Now imagine you have a unitary operator u which on this vector and it gives a complex number which is e raised to power i5. So this unitary operator have eigenvalues which are of this form. So this phi is a eigenvector and this is eigenvalue of unitary operator, and this phi is a phase. This phase we have to estimate, right? So, and this is not known to us, right? But we have some black box which apply this U, right? And here the control is 1. Okay. So how this phase estimation? So you prepare, you initialize you have two kits. You have initialize one in 0, another one is in 5. Now this, then you perform this Fourier transformation on first qubit. So Fourier transformation is in case of 2, n is equal to 2, which is n small 1. So this is a transformation matrix. So you have this one which generate equal superposition. So this equal superposition. See, we also see same equal superposition here also. This gate, when you pair Bell state, same superposition. Here the only the difference is there is a minus sign. Here is the plus sign. So you apply the Fourier transformation, you generate equal superposition. The second qubit stays in the same state. So at this point of in the time, so this is the state, and then you apply control operation. Now the control is at 1. So if you if the first qubit is 0, it don't do anything. If the first qubit is 1, then it applies this U operation, which gives this phase factor phi here to 1, right? Since this eigengate it stays at is now they are not entangled. Then you apply inverse Fourier transform, which is again same in this case, and then you bring the phase here, right? Now you can see there's this factor, right? This one, this is proportional to cos phi, right? And this is proportional to sin phi, right? So when you perform measurement, you get a cos times here sin phi, and then if you perform measurement on this first qubit, you will get phi, provided you perform enough number of measurements, right? So that's how you estimate phi. So this is a circuit. Now you are estimating phi, you are estimating eigenvalue of u, I mean same thing. Now when the same circuit is used in period finding, right? You have to find a period of like some auxiliary function, and that period finding algorithm is used in Shor algorithm, vector finding, right? So those are a bit more technical. I am not going to give you, but basically see, power is Fourier transformation. Fourier transformation is used in phase estimation. Phase estimation is used in period finding, and period finding is used in factorization. So that's how they are related. Now there's one more algorithm which is HHM, I guess, right? So this algorithm, you can find eigenvalue of any operator, right? And since you can find eigenvalue of any operator, basically same like you find the eigenvalue of U tree in this case. So now this algorithm is basically the same setup, same subroutine is used. So if you can find out eigenvalue of any operator, and provided eigenvalue are not 0, that means that you can invert that matrix or invert that operator, and that's how you can solve linear equations, right? So set of linear equation is if you can some if they are independent equations, then you can solve set of linear equation. That is the thing people use to find find the inverse of a operator or of a matrix, and to solve a set of linear, and which is this HHM, I guess is the name of this algorithm, HHM or HHM. So this algorithm is recently very popular machine learning, because in machine learning you have to process a set of equations, and once you can find the solution of linear set of equation, and that then you can use that one in quantum machine learning. So the same setup. So my point here in this talk is I don't give you many details, but I give you basic idea and basic element so that they are used in different places. Same thing. different places so that you don't get confused. So this is the whole thing. Only the Fourier transformation and then phase estimation. Then you can make everything from here. So you see this here. I tell you this the application is Shor algorithm, and application is in this quantum machine. Now let me make a small slide like power of quantum computer. So what I told you before is basically there are two things like which I use for power. So first one is superposition principle, which basically saying that that this J is one of the, J like this in this form. These are bits or bits you can say. So these are n-bit state, right? So that 2 raised to power n possible such state, right? So the superposition is basically saying is consider all of them together, right? It can take linear combination of all of them, and then processing this side is processing all of these together. So without adding any extra hardware, it is parallelization, right? So if you have that many number of states, right? So you need 50 qubits to process it. That's why this exponential power comes in the picture. The another main point is which part of superposition in some sense. So there are infinitely many distinct possibilities to perform measurement. Like as I told you, in blocks, each direction, each axis, right, in 3 dimension correspond to one measurement, right? So there are infinitely many directions, right? You can perform measurement, right? So these are because if you do in conventional conventional computer like this one, so we can only measure 0 1 0 1, right? So it's only one possibility. So you can measure in any direction. So that is the power, and this is basically the superposition principle. But like this bit more technical, I will not explain it more. But this is also related to superposition principle. So many possibility of distinct measurements, right? Now the entanglement. Now what is the entanglement? Is basically superposition plus factorization, right? So there are two subsystems, right? So you just consider you are talking about the two subsystem. Now you have this state which have correlation in every direction. Correlation because there are measurement in every direction you can perform. So you have a correlation in every direction. So you have your correlation is true, right? So because if you take 2 points, right, you just glue them together and let's head and tail, and if you toss them, then there is only one possibility because there is only one direction to measure. But there are in any direction you will see this anti-correlation. So that's why this correlation is stronger. And in a bit more technical term, so there is something called Bell inequality, right? So Bell inequality, if you take a correlation which is come from this this conventional computer, so that Bell inequality, the correlation is not so strong, so it always obeys that Bell inequality. But if you take correlation based upon such states, you violates Bell inequality because the Bell inequality set a limit on a correlation. So this quantum correlation goes beyond that limit. And just want to emphasize one more thing. This Bell inequality is also used in security proof of this quantum key distribution protocol. Okay. So if you see this Eckert paper, this proof is on Bell inequality, security proof. Well, because you take half the data, and if it violates Bell inequality, that means secure communication. If don't violate Bell inequality, then it is not secure. So these are the two main powers of quantum computers. Now let me tell you one more application where superposition plays a very big role. This is a Grover search algorithm, a quantum search algorithm, right? So let me tell you what is the search. Suppose you have an item and this is your database and this is unsorted. So they, so J is associated with maybe tiger, n is associated with apple, and then 1 is associated with the TV, let's say, right? So they are, there is no structure, right? And you are looking for one particular item, and it will be one of them, right? Let's say it is K, right? So that's how you like if you do it on conventional computer, and how you will do it. You just say you just pick one and say whether this is the item which I'm looking for. Answer is yes, then you stop the search. If answer is no, then you pick up next two and then ask the same question, and then you pick up like this, and then in general you have to, on average you have to go through half of the data n by 2 number of item before you get the result, because each item have a half probability to be your item or not, right? In worst case you have to go through n minus 1 items, right? So it's a linear in n, linear in data size, right? If you have a billions of item, so you have to go half of that, right? To find out your item. Okay. Now, what is quantum search is this is the process, right? So basically, you take all the item and create equal superposition of them, and this is like 1 by n is the amplitude, and the square will be the probability. So 1 by n is the probability for each item in the beginning. So basically it's a uniform distribution, right? So any one of the item can be the your item which you are looking for. So now I can rearrange in this way. It's just a mathematic trick. So basically what I have done is I have write them this one into two parts. One part is where my item belongs. The another part is where is orthogonal to that, where it don't belong, right? And then I arrange these factors in such a way that this square of this one and this one become one. So I can very well write this part as a cos with some angle and sine with some angle, and for convenience I just take angle theta by 2, so you can take theta, it doesn't matter. So basically you are rearranging the same thing in this way now. Now this Grover operation is, now you have a two-dimensional space. It's just like a qubit. You have n dimensional space, you turn into two parts, which is like where your item belongs and where it don't belongs. Then you end up into k and k orthogonal, which is a two-dimensional space, which is qubit, right? So you can write this whole thing in this k orthogonal and k basis. So you will get a column with the two entries. Cos theta is first one, correspond to k orthogonal, and second is sin theta. Now this Grover approach operation, right, you read in the books, is a complicated one, but it basically is a rotation in these two, right? N number of items, and also depend upon how many items are there in your database that matches query, right? If you are looking for maybe, let's say, tiger, how many times tiger is there, okay, or how many different tigers are there in the database, okay. So anyway, so now this is a rotation, and then if you do simple mathematics, is this angle increase. If you do multiply this one, this is the simple matrix multiplication, and this is a single iteration. And after m number of iteration, the angle become m plus 1/2 times theta and cos here, right? So see, these are the amplitude, and as I told you that their square will be the probability. So the square of sine this angle will be the probability of finding this state, right? And 1 minus the probability will be the cos, which is finding this one. And we want this probability to be 1, right? So we want this to be 1, which basically means like m be equal to pi by 4 under root n. So it's just a simple thing, like you just apply Taylor expansion and things like that, you will get such under root n. And where it basically comes from, because here theta is related to 1 by under root n. See here. So this part, right? So you can see that if you just randomly pick an item and search, then it will take average n steps, and here under root n, right? So this is called quadratic speedup, right? So you can do it search algorithm. So basically what you are doing is you are in each iteration you are decreasing this amplitude, you are increasing this amplitude. Basically you are decreasing this probability and you are increasing this probability, right? And in the end, after running that many iterations, you will get a, you will perform a measurement, and most likely you will get this result, because this is very, the probability is very close to 1. Okay, that's how you complete the search. And where it is used, I mean, this algorithm is also called amplitude amplification algorithm, and this algorithm is recently used in portfolio optimization, right? Suppose you have n asset, right? N number of assets, like you want to invest in maybe in some one industry and some other industry with some amount, right? So this amplitude can be thought of a amount you want to invest in some industry, right? So initially you start from the, you want to, you take all those things equal, and then you apply that some amplitude rise, some amplitude smaller, and that's how you optimize your, like you have $1 billion, you spend some of them in asset 1, some of them in asset 2, and then after running this algorithm, I mean, this is a part of that. So you get the final, this vector is give you the fraction of $1 billion you invest in one, fraction of $1 billion you invest in second asset, and so on. So this is one application, is a portfolio optimization. I mean, it's have another application also, but this is one of the recent application. Sorry, I forgot to put that paper where they use this Grover algorithm for portfolio optimization. Right now, that is all what I want to say about gate based quantum computation. Now I just go to the next one, adiabatic quantum computation. So if you have some question, please ask. Okay, so I go next. So adiabatic quantum computation is, this is basically in D-Wave, this quantum computer company in Canada. I mean, they use this kind of approach to process information. Okay, so what is the approach? The approach is you take a Hamiltonian. So you have a single qubit, which is a two-level system. So in physics is basically a function which define energy, which give energy of the system, right? Now this Hamiltonian is made up of these two parts, x and z. I mean, this is the same x gate which do flips, right? Convert 0 to 1, and this is a phase gate, you can say z, right? Or these are called poly x operator, poly z operator. These are flip operator or flip gate or phase gate. I mean, they're the same thing. Now this Hamiltonian combination of two parts, this is a convex combination, t and 1 minus t. T goes to 0 to 1. So when t is 1, then h is equal to z. And when t is 1, when t is 0, then h is equal to z. And then when t is equal to 1, then h is x, right? So okay, so you are changing your Hamiltonian, right, from z to x by changing this control parameter t from 0 to 1, right? So this is a 2 cross 2 matrix which you see here, which is have a parameter t which you control, which is in your hand. You want to change it. Now you can find the eigenvalues of this matrix, which are these, and basically the energy of the system. Eigenvalue of Hamiltonian are energy, and then eigenstates are the energy levels or energy states, you call it. And if you plot these two energy as a function of parameter, they change like this. So this lower one change like this and upper one change like this, right? So usually the lower one people call it ground state, and top one is first excited state. And if you find the eigenvector of this Hamiltonian, so corresponding to this ground state energy, this is a minimum energy because there is a negative sign. So this is the eigenvector corresponding to ground state energy. So I write in terms of again rotation because it's easy to explain things in rotation. So throughout the presentation, you'll see every time I talk about rotation. So here this angle theta depend upon t in this way, right? So you take a cos inverse and then you divide by 1/2, then you get an angle theta as a function of control parameter, right? So what adiabatic theorem says is that if you change t slowly enough, right, then if you begin with the ground state, if your initial state is this one, right, ground state for t is equal to 0, then it will stay in this state. See, this state is a function of t, right? It's changing with the, like Hamiltonian is changing with the time, or time, this control parameter t. Then this because of this state is also changing. Also eigenvalues are changing, right? So you see that if you prepare at t is equal to, or in this state, so it will stay in this state, which of course changes with the time. And how slowly you go, how slowly you change t depend upon this energy gap. So you see there's an energy gap here, this ground state and excited state. If this gap is very slow, very small, then your change must be very slow. Otherwise, your system will jump from ground to excited state. Okay. So the gap is, so you just speed with which you go here. So that's how, if you change from t0 to 1, so you start from the ground state of x, you end up in the ground state of z, right? So here it is easy to say the ground state of x, sorry, I say wrongly. This is, you start from the ground state of z and you end up in ground state of x. So ground state of z is this the south pole, because 0 is a excited state and 1 is a ground state. This is south pole, and it goes to negative x direction. So you see this x is positive x and -1 in this direction. So it goes like this. The state goes like this. So this is a trajectory. I'm representing trajectory of this state I'm representing here, and trajectory of eigenvalue I'm representing here, right? So that's how you change, by changing the control parameter with speed that depend upon the gap, inversely proportional to the gap. Gap is smaller, speed will be smaller. Speed is faster if gap is large. So that's how people use this one in D-wave computation. So let me tell you a bit more concrete what is the D-wave system is. This is the D-wave system. So this Hamiltonian, like before, have two parts. This is X part and this is a Z part, right? And the X part is a sum. You have a n qubit or n spin. In this case, I take all 8 spins. So sorry, I just write it somehow wrongly, but this 1/t factor should be here, and this t factor should be 1/t factor should be here, and t factor should be here. I mean, but basically what I want to say is, like, at the beginning it is x. So sorry, I just, like here I write it reverse way, but I think you can understand why. So there is a little mistake here. So 1/t factory here and t factory here. So initially, the system, this is my Hamiltonian. This is part like where all these spins are, like in pointing in x direction. If I put 1/t factor here, as t is equal to 0, then 1 minus t factor here is give this part will be 0. So all these spins are in x direction, pointing in x direction, then you suddenly slowly change this t, and then you end up you are increasing this part, which basically says that there is an interaction. This omega is this W is the interaction strength between ith spin and jth spin, right? And these are interaction, mutual interaction between spin is favored in z direction, and external field is applied in x direction, right? So you prepare your system in the ground state of this one, x, which is in this direction, and then you slowly change, and then this part goes to 0 if I put 1 by t here and t here, and then this part survive. So you end up the ground state of this, right? Now, what is, how I can use this one to make a application? So the ground state of this part, right, is the one which encode the solution of my computational problem, which I will describe in the next slide. What kind of computational problem I can consider. So ground state of this red one have the solution of my computational problem, which I want to optimize. And ground state of this green part is the ground state which I can easily prepare. Like these are not correlated, these are polarized in x direction, so I can easily prepare ground state of this one, and then I slowly change. And this finding ground state of this Hamiltonian is very difficult, NP hard, which of the example which I will send next slide. So this then I slowly change, and then I find the I reach the ground state, which is the solution of my problem. So this kind of model is called Ising model. It's in physics. So there is a book on quantum phase transition by Professor Sachdev. So you can see such kind of models in this book. Okay, and now I go to the problem, right? So this is such kind of problem you can solve, right? So this is a vehicle route optimization problem, right? So imagine you have 10 customers. So this blue points is 1 to 10. So these 10 customers say that we want to transport a load, like some amount of weight, or from one place to another. For example, this customer 5 want to travel some weight from here to this point. Customer 1 want to travel this way. Customer 3 want to travel in this way. So you have seen traveling salesman problem. It's a generalization of that, right? Because in traveling salesman problem is you imagine have a newspaper seller. So he goes to the warehouse, he take all the newspaper, and then he distribute. He goes to point 1, 2, 3, 4, or first he go point 1, then 5, then 6, then 7. So in any order, these 10 customers, he just deliver. Now here, this vehicle routing is you have to pick up and then deliver, right? So imagine you have only 2 bicycle to do that. So 2 trucks to do that. So in traveling salesman, there is only 1 person who is doing it. So imagine you have 2 person. So you have to find a route which can take all the weights, and then the total amount of weight should not be more than the capacity of the vehicle. Otherwise, you cannot carry that weight, right? And it must visit the pickup point, this blue one first, and then delivery point later. And then such kind of problem you can encode in this Hamiltonian, part of the Hamiltonian. So, and once you find this minimum ground state, which give you minimum energy, and by the way, this W will be the distances between these 2 points, right? So these W will be the distances between these 2 points, which you want to minimize, right? You want to minimize is this energy, ground state, right? So when you just change T from, there will be 1 minus T factor, sorry again, T factor here. So you just change this T, and you end up in the ground state of this Hamiltonian, which give you minimum energy, which give you basically the minimum distance traveled, right? And then you get this solution. So this one set of trucks is this one. So you the one path for first truck is you go start from 3, then go to 8, then 18, then 10, then 3, then 6, then 1, and then so on. For green truck you start from 2 to 9, 9 to 19, and 4, and then 5, and this is the another route. Imagine, because there are many possibilities, and you know the permutation, there are many permutations. So for n trucks, this is n factorial permutations, right? Roughly speaking, for traveling salesman. So an n factorial is much more big number than 2 raised to power n, right? So you know it's even more than exponential complexity is there. So that's why it is called NP hard problem. And if you have 100 customers, if for a big travel company, then it is almost impossible. I mean, like if you give this program to a human being, he cannot find the best possible path, right? You need computer, and you need fast computer, because you want to make this, because this is NP hard problem. So in this paper, right, in this paper they formulate many NP hard problem in icing formalism, which you can run on adiabatic quantum computer, such as these, right? So this is one of the application of and then again you can use same thing in portfolio optimization, and you can, you know, this combinatorial optimization can be performed uh, there are many things like drug discovery, and Nagendra told you many possibilities. So all of these can be deal like this, right? So that's all I want to say. So what I tell you is basically, I tell you how to, what is the basic principle of random number generator, what is the basic principle of quantum cryptography or quantum communication, what is the basic principle about factorization algorithm, which is Fourier transformation and phase estimation are two parts. What is the basic principle of quantum search algorithm, which is, you know, like also amplitude amplification algorithm, which is used in portfolio optimization. And these I tell you how to use it with the gate based quantum computation model, and then I tell you other problems such as a traveling salesman or combinatorial optimization, which you can do it with this adiabatic quantum computation or any link based quantum computation, which D-Wave use. So that's all I want to say, man. Thank you so much. So if you have some question, please feel free to ask.
Dear participants, if you have any queries, please unmute your mics and ask, or else please type in the chat box. Still, we have 10 minutes of time. If you have any queries, please feel to ask.
So, by the way, I just want to tell you, this is what we have done in QPI recently with 500 customers. So,
Hello, sir.
Yes.
Sir, thank you so much, sir. Thank you for accepting our invitation and presenting nice presentation, sir.
Okay.
Gate-based computing. Uh,
Okay.
Sir, thank you, sir. Thank you so much, sir.
Okay. Then you can ask me later or send me email or something, like if you have more queries or want to know more. And thanks to you, I mean, for organizing this and giving me this opportunity. Okay.
Thank you, sir. I will share your email ID with you with the participants, sir. If
If,
anybody want to ask any questions to you, they will mail to you, sir.
okay. Then thank you and
Sir,
have a good day. Yeah.
thank you, sir. Sir, kindly share your PPT with us, sir.
Okay, I'll send you this PPT if you want. I mean, like maybe I can. So we the same email address. I just like I get this invitation and then same email address. I just send the PPT.
Yes, sir.
Then
Yes, sir.
the person
Eh,
can. Yeah.
Yes, sir. Yes, sir. Thank you, sir. Thank you so much, sir.
Okay. Bye, and
Okay,
have a
sir.
good day. Bye.
Thank you, sir. Bye, sir.
Bye.
Dear participants, our next session will start at 11:30. Let's have a break. Thank you all. Manager experiencing international. Why? Sir, uh, it's my privilege to welcome you, sir. Sir, please hand over the session, sir.
Thank you, Bhavya. Thanks a lot for such a kind introduction. So let me begin by saying that I'm not alone here. I'm with my colleague Pinakin. He is in the list and he can say hi maybe.
Hey.
Hi, Pinakin.
Hey.
Yeah. So we have divided the presentation into two halves. In fact, I would be giving a very, very preliminary, a very basic overview of basically qubit hardware. On the other hand, Pinakin will actually dive into what we are doing at QPy AI to be more detailed. So let me begin with my presentation here. I present now. Let me see if I can do this. Yes. I hope you can see my screen. Pinakin, can you confirm?
No, not yet.
No, sir, not yet visible.
Yes, now it's visible.
Sir, now it is visible, sir.
Thank you. Thanks a lot. Yeah. Okay. So, so how do you make quantum computers? So we have been listening about, I hope, quantum computers for last 2 days, and now we come to a point that we have to actually make them. Unfortunately, this would not be very technical. Will be very simple. So my overview would be basically why go quantum. We have good classical computers, the computer that we are using right now, and so I will introduce why do we need it, motivate. So why do we actually need such quantum computing devices? Actually, it's based on the two superpowers that we have from our quantum world, which are superposition and entanglement. And then I will describe what are the different kinds of qubits that we have, and how does and then I go on to say how does a quantum computer look like, and we will show the QPy approach that we are taking. This picture that I show over here is actually the approach that we are taking at QPy AI. So I will describe that too. And then I will actually finally hand over to Pinakin to go detail on really what and how the qubits are controlled and how do we do that here. So let's dive in. So yes, so why go quantum? The point is that nature itself is quantum. We don't really appreciate it on day-to-day basis, but the fact that we are having solids around us, for example, the chair that we are sitting on, is basically coming from the fact that the atoms are very hard. When I say hard, why? How can you say that? Because inside atoms, the electrons are distributed in levels. They are not all going and collapsing into the nucleus. This is because of quantum mechanics. So there are different, for example, here you have hydrogen atom. This was simplified picture. You have different levels, energy levels with different wave functions of hydrogen over there, and they are having space between them. So the electron cannot collapse into a nucleus. So, and then on top of that, we have Pauli's exclusion principle. The two spin up electrons, spin down electron cannot be at the basically no two electrons can be in the same exact quantum state. So either it is spin up or spin down. So that means only unique states are filled in an atom. That also gives it a rigidity. So atoms become hard. So as a consequence of that, we have solids, because then we have molecules. Molecules are also becoming hard. Then we have large molecules. Then you have your fibers in your wood, and that's the chair. Another example is exactly you have a variety of such similar, characteristics from just like snowflakes. So just from the fact that we have water and molecule, and we can have different kinds of snowflakes, different structure, variety of nature comes out. So if you want to simulate nature, we have to go quantum. This is not said by me. This is by famous Richard Feynman, 1982. He was saying nature isn't classical, damn it. And if you want to make a simulation of nature, you better make it quantum mechanical. And by golly, it's a wonderful problem because it doesn't look easy. So there are two things here, that it is not easy to simulate nature. Nature does it effortlessly, of course. On the other hand, we have, if we want to do it, we have to do it quantum mechanically. Therefore, we need quantum computers. The direct consequence of this is that, for example, if you have a drug, or if you want to discover a drug or invent a drug, for example, in this case, I would say, let's say an antibiotic. The way an antibiotic works is that it goes inside the ribosome of a bacteria and attached to it, such that it doesn't make any protein. So it makes the protein synthesis. It inhibits the protein synthesis in bacteria. However, it doesn't do it for human cells. That is strange, because what it has is the ribosome of human cells is a little bit different, only a little bit different from bacteria. So it's really very critical to get the structure of the antibiotic correct. That is how that drug is an antibiotic. Other drugs are different, doing different things. That is the main point of being antibiotic. Now, the structure of antibiotic is very critical. So if we know that, so how to make antibiotic, if I can predict the structure of antibiotic very correctly, then I can make a very new and efficient antibiotic that will not have any side effect, that will not harm humans. On the other hand, it will be very hard on bacteria. But this kind of real bottoms up approach, that I put structure atom by atom and then build really an efficient antibiotic, cannot be done on a classical computer, because these atoms, these molecules, these complex sheets that we see right over here are all quantum mechanical. They're not. They can behave at certain times like you can think about them as classical, but they are not. And also on the same line, you can do material research and many more applications. I hope that you've already learned about them in the other sessions. So I'm not going to talk about them. So we need quantum computers. So why quantum computers are powerful? So we keep on hearing this thing that quantum computers are very, very powerful, very nice. Just I showed you that, okay, you need it really. So the idea behind a quantum computer is that you in classical computing, you have either 0 or 1. This is our digital computer, again, just like the computer I am using or you are seeing through. But in quantum mechanics, what you can do is a superposition, which is a term here, superposition of 0 and 1, meaning it's like a flip of a coin. If I say it's a heads and a tail, then this the quantum bit is actually flipping very fast. And we don't know 0 or 1. It's not like flipping the coin classically. It is really quantum mechanically that you cannot know until and unless you make a measurement. This is quantum mechanical. That so we really don't know, is it 0 or 1? It might be a combination of that. That's the most interesting thing about it. So I will show again later on how it is done or how it is represented in physics or in quantum systems. Right now, most important point I wanted to say that we can make superposition of 0 and 1. Therefore, all possible combinations of 0 and 1 is possible in quantum mechanics, and therefore in qubits. Another phenomena is called entanglement. This is even more unintuitive. You don't find it in classical world. But I'm trying to give you an intuitive approach to this. This is just take it with a grain of salt. This is not the whole picture. This is not the right picture. This is just to understand it. Maybe the point is that if I say there is a red qubit and there is a blue qubit. This is dark blue, but let's say it is blue. Yeah. And if you make them closer and closer, since they will interact with each other, what will happen is they will become entangled. This is again a technical term, entangled, but I represent here with a pink color. Because if you add red and blue, you will get pink. Interesting thing about this color is that's why I chose pink. If I zoom in on a computer screen, you will see that the pink actually never exists. It is essentially blue or red pixels side by side, right? Basically blue and red pixels. They're not like pink pixels coming out. And this is true in nature, actually. I mean, this is why I show this, is because if you say white light has pink in it, that's wrong. If you do a spectroscopy on that, you will see 7 colors, 8 Vivgeo colors, but you will never see pink. Pink actually is an optical response of our eye to combination of red and blue. That's why I chose pink. Okay, so next, what you do, you separate these two qubits. And if you do it and then measure, what you will find is a very surprising thing. Either you will get this one qubit red and the other qubit blue, or the first qubit blue, second qubit, but never this pink. And also that if you do once the measurement on red, the other qubit will automatically become blue. If you find the second one red, the first one is automatically blue. If you find the first one blue, the second one is automatically red. And this thing is really very magical. You can call it a kind of a magic. And this is combining the previous thing, superposition and entanglement. We can have qubits and quantum logic, and then we can process data like quantum data, and then we can have this maybe like this can be presented at some superposition of these two states, and it comes out in a different superposition of these two states, and a measurement could be done, and this could really solve problems. Again, an interesting way to think about it, what kind of problems and how this can be solved. So, for example, we want to find a needle in a haystack, rice hay, this rice husk or haystack, and then there is a needle in it. So it is a very difficult problem. Classically, the way to do it is go with a magnifying glass and look for the needle. A quantum mechanical sense would be, the way nature will solve it, for example, is that if I put the entire thing in water, what will happen? The hay will just float on water and the needle will sink in the water. So in that way, we have solved the problem by adding water. This is one way. So we are not going to do something like that, but quantum mechanics essentially works like this. You have a lot of qubits. You have a problem defined and you have to find exactly the state in it, which would be your solution. You do a quantum logic gate on everybody. So all the qubits that you have are entangled, and you do some quantum logic, and what you get out is your answer. So it's like looking through the entire library to find the one page that you are looking for in one book. So it's all at once. So you read the entire book at once. This is an interesting thing that we have. So it is inherently parallel. You can really do real life problems once again, like optimization, traffic optimization, finance, portfolio management, drug discovery. So there are many applications. So these are two superpowers that we can use in quantum computers. But how to really make it? Okay, people have already started making it. So qubits that I just said, that plus minus one state, there are different kinds of qubits. You have superconducting qubits in like from Google, IBM, Rigetti. So these are companies which are actually started making small or even I would say 50 qubits quantum computers. So these are based on superconducting circuits. These circuits are made up of aluminum and but the aluminum becomes superconducting at the temperature that they operated 10 to millikelvin. These temperatures, these circuits become superconducting, and these are basically oscillators. These are basically like an LC oscillator. So this will have a resonant frequency. And then they will have two levels. That's what I will describe later on. Yeah. So the other kind is going on silicon wafer. One can define spaces between electrodes where electron can be trapped, and this is known as quantum dots. And this you can use to also manipulate your quantum states. So yeah. Other kind is topological qubit. This is a very fancy kind of qubit in which you have a superconductor and a semiconductor at the same time. And at the interface of this, there is a state which is Mariana fermions. Mariana fermions. So these are Majorana fermions particles. So these are very fancy. These are at infancy. So this is a long way to go. Microsoft is actually working on it. Then you have a different class. You have ion traps. Why don't we use these kinds of, it looks like complicated stuff. Why don't we use ion itself? For example, you take an atom, ionize it, and put it in vacuum. Why don't we use that? Yeah, so people use this kind, and IonQ, Honeywell, they are trying to do that. So, and then we can also, of course, use neutral atoms. Instead of ions, you just don't ionize them, you just put it in vacuum and look at neutral atoms and make them superposition using lasers and other things. You can also use light totally. But each of these things have their own problems and advantages. For example, while these systems work in room temperature, but they work in ultra high vacuum. And all of this system ultimately relies on single photon detection. Not only that, some of them, like photonic, they actually want photon counting, number counting. So what I mean is that they have to differentiate between 1, 2, 3 photons and 1, 2, 3, 4, 5 photons. This is extremely difficult. If I can tell you that a 1 photon has come at this point, but I cannot tell you how many, like 4 photons is coming at this point, and next batch is 3. No, this is not done so easily in till now with the current technology. So they have their own problems. The other class is the superconducting, spin, and topological. They are all solid state, and that is much more reliable in my opinion. So we go ahead and actually build our quantum computer. We are going to build our quantum computer based on silicon. So I'm giving you a complex structure here, right? Everything looks very different, but essentially, ultimately, it is very simple at heart. What all these complicated things will ultimately give you two things: a qubit, like 0 and 1. This is like classical. However, you can mix these two. just like other thing. Mixed meaning superposition here. So you can have a wave function that you can define, and this is not classical. So then you have a superposition between 0 and 1 using some other pulse, other mechanism. In this case is our microwave pulse. So you can do quantum gating, control, and then you can of course do measurement, and that will help you. But the challenge is that you need a large number of qubits to make a usable quantum computer, and also precision control and gating. So these are challenges. Apart from that, you have to also cool down this quantum hardware is essentially sitting always inside a ultra low temperature cryostat. Here is a picture of the cryostat. One thing I want to bring your attention to is the lower stage is at, okay, it's stating 20 millikelvin, but usually it's 10 millikelvin. And this is much colder than the universe, deep space. If you go into deep space, you will get like around 3 Kelvin, I think, the microwave. So, but here you have much colder than the universe. Another important part is that if you look, like this is from Google D-Wave, this is not many qubits here, but a lot of wires coming out. So we need cryogenic electronics for this. So we have to, this is really a quantum computer at room temperature right now. They will put all this shielding in, and they will seal it, they will create a vacuum, and then this will be sitting at 20 millikelvin. There is a quantum computer, the chip is inside. The superconducting qubits, they are there inside. And then they will start, and they will measure it through this. So we want to also replace these wires with a nice chip in cryogenic at 4K, the liquid helium temperatures. Yeah, so this brings us to our company. So what we are trying to do here, we are trying to develop a full stack quantum computer based on silicon. Pinakin will tell more about this. It is based on scalable technology, it's available right now, it's not in the future. We will control our qubits using cryogenic electronics. You see our qubits are sitting at 20 millik. We are controlling with 4 Kelvin cryogenic electronics. This is also new. This is done actually not many places. We don't have confirmations even from Google that they have done it properly. Also, we add AI. So you see quantum pi is control, and then you have AI. So we also have AI at room temperature controlling this quantum computation. So it's a hybrid classical quantum approach that we are taking at QPI. Pinakin will tell you more about this. In summary, I would like to close that, okay, computers are really cool. So in literal sense, they are really like very cold, 1,000 times colder than, ice, or even more, I would say. Then it harnesses nature's superpower like superposition and entanglement. And these are indispensable tools for certain class problems because, for example, if you want to simulate nature, you will never be able to do it classical. Challenges remain to build one. But we are poised to really enter a new era of this quantum technologies that we are based on current technologies. I mean, we are not talking of future like 10 years from now. We have arrived. We are at a position where we can actually make quantum computers, and we should. So that's all from my side. Thank you. And if you have questions at this moment, I would rather like to take it. Do you have questions? Hello? Hello? Okay. Is there any questions?
Dear participants, if you have any queries, please you can unmute and ask to sir, or else please type in the chat box.
Okay, if we can also ask questions later on at the end of the, before the end of the session, but I would right now like to invite Pinakin to continue this session. So Pinakin is my colleague. He is an expert from TU Delft, Netherlands. He's now joined the company as a quantum circuit designer, control circuit designer, and qubit designer. So he would be continuing from where I left. So Pinakin, over to you.
Yes, thanks a lot, Amlan, for a nice introduction and also a very good overview about quantum systems. Let me present my screen. Okay, can you see my screen?
Not yet.
Yes, sir. Screen is visible, sir.
Okay. Okay, very nice. Okay, so let's get started, because now what we are going to do is focus more on the second aspect, which is how to make quantum computer, but with semiconductor qubits. So let me just dive right into it. And let me outline what I'm going to basically talk for the remaining part of this talk. Obviously, well, what I'm going to do is summarize the key aspects that Amlan had pointed out for quantum systems, and then translate them to what are the practical aspects of what do these requirements mean in terms of practical quantum computers, and how do we go about meeting those requirements. So what I'm going to talk about in a very short introduction of this talk. And then we are going to try address some very basic questions as to why are we focusing on semiconductor qubits. Next is, what are those qubits and how they are made in semiconductors, and how do we go about building an entire quantum computing stack using those quantum bits that we have in semiconductors. And of course, I'll end with some closing remarks talking about the semiconductor qubits and the future ahead. So to begin with, let me start with a very well-known experiment, or thought experiment, I would say, famously known as the Schrodinger's cat. And I'm sure a lot of you would have heard about it. So the basic premise is this: you have a black box which does not give any information to the environment, and in the black box you have a cat and a radioactive substance, which is basically this black box, which is going to release a poison based on certain probability. Now, until you open the box, you do not know whether the cat is alive or dead. So this, in sort of analogy, we can say, is how a quantum system looks like. And one way to represent, for example, the state of a cat, which can be alive or dead, till the moment you have not opened the box or you have got any information from the box, it's like a superposition, which is something that Amlan was talking about also in his talk, where the requirements for a quantum system is basically it should be able to do some sort of superposition which can leverage the computational power of it. So superposition simply means there is a half probability in case of the cat being alive, or there is a half probability of the cat being dead. That is one aspect of this experiment. We could also use the same thought experiment to basically talk about entanglement. Because here the states, if I talk about the cat and the poison being two systems that I'm interested in, or the two system, which would be the case when we start implementing these systems, we know that if the cat is dead, then for sure poison is released, right? Similarly, if the cat is alive, then we know that the poison is not released. So in a way, if we combine the cat and the poison as one system, then we can say that cat and the poison is some sort of entanglement, which is a fancy word for more correlation. So if you know the state of the poison, whether it's released, then for sure you know whether the cat is alive or dead, right? That is what incorporates entanglement, which is there is a very strong correlation between particles, even if they are spaced into, the corner of the universe. So when you measure one particle instantaneously, the state of the second particle is known. And even Einstein, I would point out here, and Einstein was really baffled with this conclusion of quantum mechanics, that how is information traveling so fast? But before going into all the very fine details of physics, how is this happening? It's actually not information, and Einstein was actually kind of proven wrong very recently when they were able to do experiments showing this entanglement and superposition as the key quantum structures. Now let's go on to define what are the practical requirements that come out from the quantum system. So we have talked that we need a level system, which is basically 0 and 1, and we want the system to be allow us to create some sort of superposition between those two states, and an entanglement between two such 0 and 1 systems or two qubits. So practical requirements are, of course, easy integration. We don't want systems that are so difficult to scale up that ultimately making a physical quantum computer out of that, or making a useful quantum computer after that, is kind of impossible. Second thing is basically a longer coherence times. And coherence time here basically means how long does the system stay in superposition, or in a state that we have put it into. This is important because any quantum system cannot stay in the same state forever. It is going to interact with the environment and lose quantum properties. Is the same as saying are two qubits and you open the box. So when you open the box, the quantum property is lost. Even without opening, slowly the information is going to leak out, and the system is not going to be in a quantum state. But the coherence time is a measure which talks about how long the system is going to remain in the. And so to compute or do any algorithm on quantum bits, we want systems that could stay at longer coherence times. So this will be a metric to judge upon how to design quantum computers, or what good quantum bits, for example. Thirdly, is scalability. We want the systems to scale up. You don't want a quantum computer to occupy a whole room, because otherwise it's impossible when we want, let's say, hundreds of thousands of qubits. Currently, if you look at the systems that are being propagated as quantum computers, they usually occupy really huge rooms of processing electronics required to control them. Even as low as 2 qubits, you would need an entire room to control and read out. And to achieve molecular simulations, or to achieve applications such as drug discovery, we would need hundreds and thousands of such qubits. You can imagine making a go down full of quantum computer is going to be really an infeasible stuff to do. Fourthly, we need them to be of high fidelity. Fidelity here is basically how good the quantum computer is, or how good the qubit is, in terms of when you measure it, what is the a classical analog. Oh yes, I can do it with this classical analog, which is bit error rate. You want your transistors to have very low bit error rate. For example, when you do trillions of computations, then one error should come out. So it has to be high fidelity. Similarly, quantum systems need to be high fidelity, or quantum bits need to be high fidelity to achieve a good computer out of this. And low latency simply means that you should be able to quickly do the computation. We don't want to wait for ages for the quantum computer to give us response to what questions we ask the computer. And lastly, a good to have a requirement, or a practical requirement, would be we should be able to operate at high temperature operations. As you have seen in the previous presentation, a lot of those are at 20 millikelvin, or for example, temperatures which are very low and very hard to achieve. So the good to have from a quantum computer would be, with new inventions and breakthroughs, we kind of shift the 20 millikelvin to room temperature. And then it becomes really easy to address and, make a quantum computer much scalable and feasible out of this whole scenario. So having talked about general quantum systems, two-level systems and the requirement for superposition and entanglement. I'll try to motivate why we look forward for semiconductor qubits in this next session. So one of the key things that we look for semiconductor qubits is because we have existing foundation of microelectronic design, where you can design, simulate, and also fabricate high quality electronic materials. On the left, the typical wafer with multiple of these circuits, and one of these could represent the processor that you use in your laptops. So you can imagine how the industry has scaled from 1950s to 2000, allowing us to put trillions of transistors in a small area, a millimeter square, for example. And we want to leverage these developments to make sure that we use the existing technology and foundation to build on a quantum system that can be integrated with the existing electronics. One aspect of semiconductor or silicon basically is a clean magnetic environment. You remember I was talking about the coherence times, which means to maintain the state of the system as long as possible. And one of the reasons why the state is not maintained is because it interacts with the environment. And fortunately for us in semiconductors, almost 95.5% is a clean magnetic environment, which means the qubits are not going to be disturbed for a long time. And we can put this even farther ahead with highly purified semiconductors or silicon, which could give very clean magnetic environments such that you can have even longer coherence times. To give you an estimate, the coherence times we are talking about is in hundreds of microseconds in a clean semiconductor or silicon, which is a lifetime if you're computing at nanoseconds. So a clean magnetic environment for silicon is very good for qubits design itself. Thirdly, it's of course scalability. You can imagine that the computers have come a long way from 1950s with them occupying huge rooms to your computers or to your phones, which is even more powerful than the computers that existed there. So scalability is inherently there with these semiconductor-based electronic design. And lastly, it allows for a co-integration with classical control electronics, which means even for a quantum system, when you want to talk to the qubit or do any operations on the quantum bit, we are going to use a classical interface, which means it has to go through classical electronic chain, which would comprise of, for example, amplifiers or ADCs or filters and stuff like these. Which means there should be a possibility to integrate both the quantum and the classical things in one place. And why I stress on this co-integration is because of the aspect that we have already seen in the past. If you remember 1960s, these computers, as I said, used to occupy a huge room. And one of the reasons why they were doing that is because had these individual components, which you see here, as maybe vacuum tubes or these tube-based transistors, which are kind of interconnected. And then they have all these cables behind these racks connecting the entire instrumentation and controlling it. And this picture you see is basically an automatic calculator, which was developed in Britain in 1940s or late 1940s. And you would be surprised to know that the current state of quantum computer is the same. We're kind of repeating the history that happened a long time back with 1950s, when all the systems occupied and were not integrated in one chip. It was the brilliance of, Robert Noyce and Jack Kilby to come up with an integrated way of designing electronics such that you manufacture everything, including resistors, capacitors, transistors on a single chip, and also interconnect them at the single chip, which to a Nobel Prize in the late 1990s, around 2000. So integration or co-integration in one die is a key to make it feasible and scalable. Where does these quantum spin qubits stand when we talk about scalability or semiconductor? And you can see the image on the left. With these developments of different kinds of qubits, 3D transmons, cavities, and fluxonium with superconductors, it took almost a decade to come up with a nice quantum bit, which could have bit error rate or operations per error somewhere around 1,000 operations with a single error. Whereas the spin qubits in semiconductor began just very recently, I could say 2013 or something. And already you see they have reached at the end of 2018, they had crossed the ballpark of 1,000 operations for a single error. So you can easily see that there has been an improvement in coherence times, which relates to the fact that we can purify the silicon and have a nice qubit there. Increasing fidelity is what you see in this graph here, with only one error in 1,000, and this graph is quickly rising ahead as we are talking right now. And scaling up potential is something that has been proven in the history, where we see that huge computers can be, in your pocket now, just because it has been possible to scale them up at such tremendous levels. And the good part is, of course, it uses commercial fabrication labs, which allows us to have very clean fabrication process in a standardized way of these qubits and the controlling circuits surrounding it. Now that we have looked in, motivated ourselves with the semiconductor qubits, what we're going to do is talk about what are those qubits that can be made, or the key elements. Qubits is basically the key elements that form the quantum processor. So we're going to motivate ourselves to look into what are those qubits and how people are making the qubits out of these semiconductor-based technology. And to break it down for you, there are three key different types in which people make these qubits in semiconductor. The first is donor-based qubits. Here you see in yellow there is a silicon slab, and they have, with the ability to manipulate single atoms, they have put a single phosphorus atom in the bulk, and have made an energy diagram or energy well such that you can trap a phosphorus donor electron, a qubit system, and have control via a gate which basically connects to this side of the semiconductor, which is a metal. However, you can easily see that this manipulating things at atomic scale means that there are a lot of fabrication challenges. This has been proven in the research facilities, but when you want to scale it up for a large-scale production, it becomes really difficult to manipulate single atoms and make them as qubits. Moreover, there are other challenges with control aspect of it, because you can see the controlling knob, which would be at this end, which is like a metal contact, is farther from the qubit, which means we need a higher sort of coupling and other aspects that goes into controlling these donor-based qubits. But of course, the good aspect is there is a well-defined valley splitting, so you get a well-defined two-level system in this case. The second and quite popular, coming up as popular qubit implementation is MOS-based qubits, which are very easy to fabricate. This structure is something that one would realize from MOSFETs, which is generally kind of course material for electronic design for bachelors. So this MOSFET design is pretty much standard. You have silicon bulk, and then you have an oxide gate, and then a metal connecting to it to form a metal oxide semiconductor. It's very easy to fabricate. However, the downside, it has a disordered potential. You see it has more like a triangular potential than like a 3D well potential that you can see in this donor-based implementation. But of course, because it is straightforward to fabricate, we could make some modification in the fabrication process and come up with a better design for these kind of qubits, which is for future developments and fabrication processes. The other slightly expensive way would be to have silicon germanium-based quantum bits or qubits. Here also you have silicon germanium bulk, and then there's a layer of silicon, and that acts as a qubit well, which is a few nanometer thick. It allows for low disorder because you are already away from the interface. and it gives a very nice qubit. However, there is a problem with valley degeneracy, which means the two-level system is not very well defined or split, which means you need to put in more magnetic field or do other sorts of asymmetric fabrication, such that you get these valley splits which are already there for most donor-based qubits. To give you an idea on how they look in real world, what you see here is basically a transmission electron microscope image of donor-based qubits and the surrounding electrodes. All this dark gray part is basically all metal electrons, and below this outlined yellow boxes, there are single phosphorus atoms which are doped inside the bulb, and these are the two qubits that are basically it's a double quantum dot with all these electrodes controlling the potential. And the three sets here trying to read out or see what is happening with these qubits. The other aspect which I was talking about is the silicon germanium based qubits. And here how they manufacture is this ladle shape that you see is basically trying to control the qubit which is inside the bulb. And you can easily see why they needed like a big square ladle is because the qubit is in the bulk, which is farther from the controlling aspect, which means they need a more sort of coupling and electronic, stronger electronic interface to make sure they are able to control and read out these qubits. And this fancy structure that is visible on the left is basically a sensor or an electrometer, which is trying to judge if there is a single electron present in this four quantum bits. These barriers that you see are basically controlling how they are going to talk to each, basically trying to manipulate the wave functions of these two individual qubits and having a voltage control knob to make sure you're having a good control over those wave functions. And lastly, of course, is a standard source, drain, and gate-based structures, which is becoming very popular these days because of the ease of manufacturability. And the fabrication labs are very happy because they don't have to make a lot of changes in the fabrication process to come up with these designs for MOS-based qubits. This is a scanning electron microscope image, but the colors are basically, it's color-coded so that you can make a difference between the source and the gates. So now that we have seen that there could be multiple implementation of these qubits, we want to focus on how are we going to use these qubits to do the key things that we wanted to do, superposition and entanglement. So on the left, you see different sets of gates that apply to single qubits. What these gates mean is this analogous, it's an analogous to the gates that we use in our classical computers, which is AND, NAND, OR, NOR, XOR. Similarly, and they do different things. Similarly, here you have different gates, which does different things on the qubit. Essentially, what they do on a qubit is basically rotate them on the block sphere. So the image that Amlan had showed in his previous presentation, saying that there's a qubit 0 and a qubit 1, or the two states of a qubit, and the qubit could be in superposition any of the state in the whole sphere. And how I represent here is basically a block sphere, and I representing the state of the qubit. And it could be any point on the sphere. Now, what these gates actually do is perform a rotation of the sphere. So you're basically doing a linear transformation of this dot, which is psi, from position which is defined by theta and phi to a different position defined by theta prime and phi prime. So any single qubit gate that you do is actually a rotation on a block sphere. Now, this could help us come up with a superposition. If you rotate all the way to between, you can see there's a half probability when you measure. It goes to state 0 or it goes to state 1. So you can create a superposition with a single qubit itself to be in a superposition of 0 and 1. Coming to entanglement or two qubit case, which is what you see on the lower part of this diagram, which is you have control NOT and control Z, swap operations. All this is possible when you can control the coupling between two qubits which are sitting next to each other. You will get this more idea when I come to the actual general qubit design, where I'll highlight the fact that how you control the coupling between these two to have overlapping wave functions to create like an entanglement or a two qubit gate for our purposes. And once we have been able to show that you can do superposition and entanglement, our problem is solved, because there we have a quantum computer which you can control these two major aspects and do all the controlling and read out of these quantum beats. And of course, it's the same as classical computers, where you need only a few gates to make a universal computer. So if you have a set of NAND gates, for example, it's a universal gate, which means you can build an entire system just using NAND gates. Similarly, for a universal quantum computer, you need to implement only a few gates at the hardware level, which can be a combination of a Hadamard gate, for example, and a control node and a phase gate, or some other combination which allows us to do both these operations in the quantum bit. So here we see how we are going to translate superposition entanglement into the qubit. It's basically allowing us to do these rotations on block sphere and allowing us to control the coupling between those two qubits that we have side by side. So this is where we come and focus on, okay, so how does that picture look when you try to implement in semiconductor? And what you see on the left is basically like a general qubit design on the left. These red dots are basically quantum bits or qubits where a single electron is trapped. These green or the orange gates, let's begin with the orange gates. The orange gates are basically called plunger gates, which control the potential or the dot potential or vary the potential in the quantum dot valley that is created here. Which is similar to creating that valley and making well-defined 2-qubit system. So plunger gates are the ones that control the dot potential. On the side, you have something called as barrier gates, and as the name suggests, they are barriers between 2 qubits in this case. And by controlling the voltage on the barrier gates, you can tune how they're going to interact. If you lower the potential barrier between these 2 qubits, these wave functions, which are denoted in red, are going to interact and perform 2-qubit operations by a set of physics rules, which need to be implemented on electronic scale. But this is essentially what a barrier gate does. Of course, we need an external magnetic field for our qubits in this, because we want the qubit to split its spin states from 0 and 1 with an external magnetic field, popularly known as Siemens splitting. And strength of this splitting depends on the external magnetic field that you use. And then a lot of other parameters which come with it, like what frequency you're going to control and how are you going to control, is basically determined also by the magnetic field that you use for splitting the spin states of this quantum bits. And lastly, now the question is, how are we going to control or operate or do these rotations on blocks that is allowing us to do single qubit gates or superposition or in the gate that we want on single qubits? And actually how we do is with an external line, which is shown here in little bit, called an electron resonance line. Here, what you do is basically supply an AC magnetic field with a certain frequency and a certain phase and a certain angle, which gives a very magnetic field which is perpendicular to the applied magnetic field, which is B0, which allows the qubit to basically rotate, as you will see in further slides where we talk about building quantum computers. It helps us to rotate these qubits, make a quantum bit in our case. And lastly, of course, you need something that can judge what is happening in this quantum bits, try to read out what is happening, in what state the spin is, and so on and so forth. And how we do it is with a quantum point contact or any sort of electrometer, which is going to judge what is happening to single electrons trapped in these quantum dots, which can be via a mechanism which converts the spin of an electron charge and read out. So these are all other technical aspects to making a quantum computer, but this is how a quantum bit array would in general look like. If you go around looking for quantum bits, you can easily see these key elements in different ways that are implemented there to form a quantum computer. Now that we have seen what a quantum bit looks like and how there has been developments in making a quantum bit and what is the general structure for the quantum bit, we'll quickly jump on to see how to build a computer when we have a quantum processor based on these qubits that we see at the lowermost stack. Then it goes from there to analog front-end and interface design, which is essentially controlling, manipulating, and reading those quantum bits. It goes all the way on the software stack, which means one has to work on schedule algorithms, hardware mapping. Hardware mapping essentially because when we design your qubits, not all sorts of coupling is accessible, which means depending on the algorithm, you map your circuit on the qubit array that you have as a quantum processor. So we need an additional hardware mapping, then a quantum sort of assembly language which converts the compiler output into a machine readable format. And all the way to the top where we as designers basically do these quantum algorithms and write high-level programs and languages to perform an algorithm or simulation, for example, that we talked about previously, making antibiotics. So how to build a quantum computer, and is there a blueprint to do that? Well, we'll try to debug this black box or a gray box or a blue box that you see here, as you can see in this popular comic strip from PhD Comics. And indeed, we do have a sort of accepted rules that was given by a person named Di Vincenzo, and is famously known as Vincenzo's criteria for making a quantum computer. And I'm going to list 5 essential criteria. One is scalable and well-characterized qubits. This is something that I was already stressing at the beginning of the presentation, that we want something that is scalable, and semiconductor qubits help that. So this is a tick mark for us. Well, we need to work on well-characterized qubits because that comes from the fabrication development, but at least we are on the right track for the scalable quantum computer. Next is initialization. We saw that we can control qubits individually using electrical pulses and gate voltages and things like these, which means initialization is an engineering problem. Depending on what quantum hardware we have, initialization is possible, and we are well into this initialization aspect. So qubits can be initialized to a known state. After that, you can do quantum computation. The third is the long coherence times, which is obvious now that we have talked about quantum computers for almost an hour, that we need systems that can preserve these quantum states for a long time to allow us to do these computations. Hence, long coherence times is one of the criteria to have a good quantum computer. Fourth is the universal quantum gates. This we already seen with a set of 3 possible gates, for example, the control NOT and the Hadamard and the phase gate. We'll be able to implement a universal quantum computer because these 3 sort of gates form the universal quantum gates that are required to do any form of gate. So a particular combination of these gates will allow us to do X gate or Y gate or Z gate or whichever gate that we desire to do. So universal quantum gates should be defined. And last measure, or the primary key criteria measure, is the measurement and readout. This depends on the electronic hardware, on how do we control and read out this circuit, which is what I'm going to talk in the this rest part of this session. But we have already put a tick mark on a lot of these aspects, which is scalable, initialization is possible, we've defined universal quantum gates, and we can see that there is a lot of development going on and fabrication side for longer coherence times and well-characterized qubits. The last part that we talk about now is basically the control and the readout of these quantum bits. And then we scale it up all the way to, what a big quantum computer look like. So coming to qubit control, what you see here on the image on the right is basically 2 spin state systems. One is the ground state and one is excited state. A lot of details are ignored here. It's a simple picture for a 2-state spin qubit system. On the left side, you see a reservoir of electron. So by controlling these barriers, basically the peaks are the barriers which are controlled by these barrier gates, which I was talking in the previous slide. And you need to have some sort of electronic pulse which can have qubits in a superposition state of 0 and 1. So it need not be in just ground state, but a superposition of ground and excited state. And how do we do that? Well, we already saw that we need a red line, something called an ASR line, which basically gives this AC magnetic field. And the characteristic control tuning knobs that we have as an engineer or as a hardware designer is the amplitude of the pulse, which defines at what rotation frequency and the qubit is going to rotate from 0 and 1. So how fast this is going to shuttle from 0 and 1. Phase, which means phase and duration, which is going to define on what rotation axis is the qubit to rotate. and what angle or by how much angle it is going to rotate in the block sphere. Of course, this one has to imagine in 3D because a simplistic 2D picture will not reveal a lot about axis of rotation and stuff like these. But this defines how you're going to rotate the qubit and if you're going to put it in superposition or not. So this is essentially qubit control aspect where a hardware designer needs to take care of designing an AC radio pulse, for example, in gigahertz range, which can achieve these superposition for single qubit gates. Coming to the second aspect of it, which is reading out. Now, you know that once you read out, the quantum system is dead. There's no more quantum system left. You are basically doing a classical projection of whatever quantum system we had earlier. So qubit readout is basically kind of destroying that classical information, but that's how nature is. We run an algorithm such that these measurements are needed, and then we perform the whole algorithm again to make sure things are probabilistic. So it's a new way of computing. But how do we do readout? Well, one thing is, if we place our systems, which is shown in this image here, where you have two spin qubit systems, and these levels basically talk about energies. And the space in between is an energy barrier. So the qubit or the spin electron's energy cannot be anywhere in this, but on this level or on this level. And the energy of the reservoir, nearby reservoir, is somewhere like this, which is in between these two energy states. This means that the spin here is at a lower energy than the energy of the reservoir, and it will not tunnel out. So if you have an electrometer which sees, oh, there is no electron coming in the reservoir, then you can be sure that the system you are trying to read is in ground state. On the other hand, if it was an excited state, what will happen is, because the energy of the qubit is higher than the reservoir, it's going to jump out into the reservoir or tunnel into the reservoir, and a lower energy state is filled after the electron has tunneled out and another electron comes in. So this exchange of electron in the reservoir can be noted in an electrometer, which is very sensitive even to single electron movements. And that's how we perform readout, because now we know there was a spin up state, which has now been initialized to spin down state. And this is exactly what I explained and what you see here. So basically, if I have to start from the C aspect, you are basically pulling the energies all the way up from the reservoir energy. Then you try to pull them down such that either the top part is occupied or the bottom spin is occupied. And we are not aware. So it's called eject and wait time. And when you want to read out, you basically place these levels such that they are in these levels. The reservoir energy level is in between these two spin states. And this is exactly what you will read in an electrometer. So if you see some sort of bump happening, that means it was a qubit that was on spin high state. It went into the reservoir and came back in. And this is how we're going to basically read out and understand what is a qubit doing. There are multiple ways. Before going into more details, I could just point out that there is something called energy selective readout mechanisms or tunnel rate selective mechanisms, but essentially they all try to convert the spin into charge. So the spin is converted into a charge, and the motion of the charge tells us whether it was spin up or spin down. Now, putting everything together, we have seen how to individually control and read out these mechanisms. And we have seen several aspects of this diagram that you see here. One is qubit design. We started off with semiconductor qubits and how they're implemented in hardware. Then we looked into some classical circuit requirements to basically control and read out these circuits and see how efficiently they can be done. We have talked about a co-integration or proposed a co-integration method also at QPI AI, which is something that we are working on. So we have a processor which is going to basically at 20 millikelvin, and then a classical controller chip, which is the classical circuits that are needed to control and read these circuits. And eventually we have a lot of optimization and a software stack, which is sitting at room temperature. Of course, later on, the goal is to start bringing these systems at a higher temperature, or start co-integrating them into a single chip, because as you can see from our experience in the past in the semiconductor industry, when Jack Kilby came up with this idea of co-integration, without that, scaling up to huge computers that you have currently is almost impossible. So that is also one of the step or key research aspect that we are looking into as a company, trying to scale it up with the current systems, and also trying to co-integrate them into a single chip. So coming down to the closing remarks that we basically kind of what we kind of learn and what we can take away from this presentation is that semiconductor qubits are scalable. One is, this is because we have already seen in the past that it has a huge potential for scaling up. And that is also something that we see in our everyday life. Phones are becoming more powerful and efficient with the same size, which means we are packing more transistors and more functionality in the same hardware. So scaling up is something that is proven for semiconductor technology, and this is what we want to leverage for semiconductor qubits. The second aspect we see is that various design challenges in terms of qubit design and integration still exist. Though we have a blueprint and an idea of how to build a quantum computer or how to go about and what are the requirements for it, there are several challenges which comes in terms of the frequencies that you want to operate in, the temperatures that you want to set, the thermal load that our system is going to give, the power that is being dissipated by these systems, and a lot of other aspects into how finely you are controlling it, what is the fidelity or how accurately your readout and control mechanisms are. All these challenges exist when it comes to an actual hardware design. And that is why you will see that generally, even all across the world, there is a very slow progress towards making quantum computers. But one thing that we are sure is that with experience and expertise, one can take on those challenges to build a universal quantum computer. It's like this: when we know where we want to go, and we have a certain set of paths that we have made up our mind for, there will always be challenges. But with experience and the sort of expertise that we bring with ourselves is going to help us build this universal quantum computer. And once it is there, everybody knows that the potential for such a quantum computer is going to be tremendous in terms of drug discovery and in terms of other aspects of quantum simulations and stuff like this. And lastly, one key aspect on why we are doing it is because it's a challenging problem, and something that was also said by Feynman and nicely quoted in Amlan's presentation, it's a difficult problem, and that's why it's an interesting challenge for us and for science community in general to address. So these are some of the references that I used for this presentation, which you can look for. And thanks a lot for your time and listening this presentation. If you have any questions, please go forth.
Hello, dear participants. If you have any doubts, please unmute your mics and ask to sir, or else you can type in the chat box. Still, there is a 10 minutes time. If you have any doubts, please you can raise.